Hi, my name is Sajal Mitra, and in this video, I'm going to talk about the RSA algorithm using illustrated examples and diagrams. This video is designed to help those who are either beginners or new to modular arithmetic and number theory. Alright, so let's dive in.
Okay, so let's start with the basics of public key cryptography. Alice wants to send a message to Bob. So how does she do that? To enable Alice to send a message, Bob sends an open lock so that Alice can send the message securely. This open lock is accompanied with a one-time key, which means that it can only be used once to lock the message. Once locked, it can not be used again to unlock the message. That is why it is a one-time key, and it is going to be used by Alice for sending the message to Bob. Once Bob receives the encrypted message, he uses his own private key to decrypt the message. This key is private to Bob, and it is not shared with anybody else. So public key is shared and used only one time for locking the message, while private key is used by the recipient of the message, namely Bob, to decrypt the message. This forms the basis of public key cryptography. Okay, so now that we understand the public key cryptography and how it works, we can start understanding RSA, which is also based upon public key cryptography. Initially, we talk about the conceptual overview without the complexities, and in due course, we get into the details of RSA. So, building on top of the public key infrastructure, we want to send a message from Alice in blue on the left to Bob in green on the right using encryption and decryption. The encryption that is applying the public key can be thought of a mathematical operation, and the decryption that is applying the private key can be thought of a reverse mathematical operation. So, to send this letter denoted by A securely to Bob, Alice raises it to the power E denoting encryption and gets B, which is the encrypted text or ciphertext. When the recipient, that is Bob, receives the encrypted message B, he performs the reverse mathematical operation B, denoting decryption, and gets back the original message A. Now let's see how this works using numbers. 3 is the original message. The mathematical operation, which we call encryption, is done by raising 3 to the power 2. We then get 9, which is the ciphertext, and the message is sent off to the other side. When the other side receives the encrypted message, that is 9, the receiver performs decryption using the reverse mathematical operation on the ciphertext, which is 9 to the power half, and gets back the original message 3. To summarize, A to the power E gives us B, which is encryption, and then on the other side, B to the power D gives us back the original message A, and we call this decryption. Let's take this forward to try and combine both the encryption and decryption keys into a simplified equation. So here we try to substitute B with A to the power E in the decryption step. So simplifying this further, A to the power E whole to the power D gives us back A. And we can simplify it further by writing it as A to the power E into D, which gives us back A. Summarizing all of the steps now, we get A to the power P is equal to A. So now that we understand the basics, essentially what we want to do is construct an elegant encryption and decryption mechanism here, which can satisfy two requirements. First requirement is instead of P is equal to 1, we need P is equal to some large number broken in two parts, that is E and D. And requirement number 2 is we need a one-way function which makes it easy for us to construct our ciphertext B, but is very difficult for our adversary to reverse engineer the original message A, even if the public key is known and the product of E and D, that is encryption and decryption key, are also known. So A to the power P is equal to A only works when P is equal to 1, as we saw earlier. Now consider Fermat's theorem. We read this as A to the power P is congruent to A mod P. This provides us a way to start with A, that is the message, and apply a mathematical operation and still get back the original message A exactly like the one shown on the left side. To understand how we can apply Fermat's theorem to find P, that is E and D, we need to have a quick look at modular arithmetic. If we take a typical wall clock or a wristwatch, we see that after it has exhausted all hours in AM, it starts counting in PM. So 1 PM becomes 13, 2 PM becomes 14, and so on. In our arrangement, we write any number larger than 0 to 11, that is from 12, outside of the clock. Note, I have not included all the numbers inside of the clock for the sake of simplicity. In modular arithmetic, we call this a mod 12 clock because it has 12 digits. For simplicity, we will call this a mod 12 remainder clock. I say this because any number n outside of the clock when divided by 12 will result in a remainder corresponding to that number line. For example, on 3 o'clock, we have a rectangle which denotes the number line, and it will give us the remainder 3 for any number divided by 12. So 15 divided by 12, the remainder is 3. Similarly, 27 divided by 12, the remainder is also 3. An important thing to consider here is that for 3 divided by 12, remainder is again 3. Now consider a mod 3 clock. We will be using this mod 3 clock throughout this presentation for simplicity. Similar to the mod 12 remainder clock, after we have exhausted labeling till digit 2 inside of the circle, we begin labeling outside the circle in a clockwise fashion. Now, on the digit 1 number line, if we divide any number n by 3, since it is a mod 3 clock, we get the remainder 1. Example, 4 divided by 3 is 1. Similarly, 7 divided by 3 is also 1, and so on. On the number line 2, we get 2 as remainder if we divide any number n by 3. Note, if we divide 2 by 3, we get remainder of 2 itself. So we see that for mod 3 remainder clock, we have 0, 1 and 2 remainders for any number line. Fermat's little theorem says a to the power p is congruent to a mod p, where p is equal to prime number. Let's take digit 2, that is the remainder inside of this mod 3 clock, and rotate 2 times. We arrive at digit 8 outside of the clock. Effectively, even after 2 rotations, the remainder is the same. This is exactly the kind of desired effect we wanted to achieve for our naive example earlier when we took p is equal to 1, consisting of e and d, that is 2 and 1 by 2. Simply stated, if A is the original message to start with after encryption and decryption operations, we can get it back simply by rotating the mod p clock some number of times. This method works great for prime numbers p, but we want this scheme for any number. So inside of Fermat's little theorem, instead of mod p, that is prime numbers, we want mod n, that is any positive integer. So in order to get mod n, we tweak the Fermat's theorem, and dividing both sides with a, what we get in the red box is a special case of Euler's theorem, where p is a prime number. We then arrive at Euler's theorem by replacing p minus 1 with phi n, which is Euler's torsion function, and we substitute mod p with mod n being any positive number, co-prime with a. Euler's torsion function is the count of positive integers up to a given integer n that are relatively prime to n. The torsion function helps us in construction of E and D, that is encryption and decryption keys. More on that shortly. Now remember, we need a mechanism to start with the original message, that is A, and get back to the same message using the remainder clock. But Euler's theorem doesn't quite gets us there. So we need to tweak the Euler's theorem by multiplying it with a on both sides. This now gets us back to the original message a on the right hand side. Now let us examine the one-way totient function. So we start with the modified Euler's theorem, and inside that we have the totient function. Totient function denoted by phi n calculates all the integers less than equal to n which do not share a factor with n. Example, when n is equal to 5, there are 4 integers from 1 to 4 which do not share a factor with 5. However, for phi 8, we can see that 2 and 4 are excluded as they share a factor with 8. We have also excluded 6 because 6 shares the factor 2 with 8. For prime numbers like 5 and 7, phi n produces results n minus 1, which is simple to calculate. However, for non-prime numbers like 8 and 15, there is no easy way of computing phi n, but manually. A great feature about Euler's totient function is that it is a multiplicative function, meaning if two numbers a and b are relatively prime, then phi ab is equal to phi a into phi b. For example, to compute phi 15, it is easy to do so using the simple n minus 1 method to calculate phi 3 and phi 5 as shown here. Now if we try to calculate without this method, with n being non-prime, we have to manually compute phi 15, which is very hard. So this becomes our one-way function. So in the modified Euler's theorem, the encryption and decryption keys are together inside the phi n plus 1 power of a. But this is rigid since for a given mod n, we can have only one way of computing ED, that is encryption and decryption keys, which is phi n plus 1. We somehow need to scale this phi n plus 1 to different values so that we can compute ED with other combinations for a given mod n. Let's see how this can be done. Consider again the mod 3 clock with Euler's modified theorem. In this example, we can multiply phi 3 with integers, example 1, 2, 3, 4, etc., and get different values. If we multiply it with 1, we get 2 to the power 3. The clock hand then rotates 2 times to 8. If we multiply it with 2, we get 2 to the power 5. The clock hand rotates 10 times to arrive at 2 to the power 5, that is 32. Similarly, if we multiply it with 3, we get 2 to the power 7, and the clock hand rotates 42 times to arrive at 128, which is 2 to the power 7. Generalizing this, we get k as a multiplier to phi n. Hence, we clearly establish that multiplying k to phi n on the left side has no effect on the right side of the congruence operator. This is because we only work with remainders in the remainder clock. So introducing k in Euler's modified theorem gives us this final equation which helps us calculate encryption and decryption keys. In the previous slides, we started with the modified Euler's theorem and thereafter introduced the variable k in the theorem using our remainder clock mechanism. To prove this mathematically using equations, we start with Euler's theorem and arrive at the same result in the end. Although this time we introduce the variable k one step before we multiply a on both sides of the congruence equation. Next, we extract the encryption and decryption keys. So we start with ED is equal to k multiplied by phi n plus 1, and we get the decryption key as d equal to k into phi n plus 1 upon e. Now we can calculate the ciphertext C from our original message A using a mathematical operation. We then send the message to the recipient. The recipient uses the reverse mathematical operation on the ciphertext C to get back the original message A. Now let's see the RSA in action. A is equal to 2 is the message to be encrypted. We consider remainder clock of mod 15 since it is made up of two prime numbers, that is P and Q, in this case 3 and 5 respectively. We choose the public key, that is E, as 3 and the multiplier K as 4. The decryption key is calculated as 11. Now we are ready for encryption and decryption process. The sender encrypts the message using public key, that is 2 to the power 3 mod 15, which gives her the ciphertext C is equal to 8. Upon receiving the message, the receiver decrypts it using his private key on the ciphertext, that is 8 to the power 11 mod 15. This gives us back the original message. If you found the video helpful, please hit the like button and thanks for watching.